And let's start with how the term is ending, okay? I know this is a day you've all been dreading all term, the last day of class. Sorry about that, but it's almost over. I'll be here all day today. I have this class and my next class, and then I'll be in the office from sometime after 5:30ish or so until 6 o'clock. So anything you want to turn in to me today, I'll accept until 6. Anything after that, if I'm not here, slide it on my door and I'll take it then. Okay. Tomorrow is the last day for Tuesday, Thursday classes. Okay. I'll be here from 8 to 8:30 in the morning. You can turn things in to me then. I'll pick up anything that was slid under my door before then. Then I'm in class from 8:30 until 10:45. And then from 10:45, I'll be in the office until about 2 to 2:15. I've got an eye appointment tomorrow. It was at 2. They moved it to 2:15, so it's just right across the street here at UAB West. So I'll be going over there. Last time I sat around for almost 2 hours. I can't do that this time because I need to leave from Bessemer by 4 to be able to get to about 4:30 to get to my class at 5 o'clock on the Birmingham East Campus. So I'll probably be out of pocket pretty much from 2 to 2:15. I hope to get back to my office sometime, but I won't be here long before I have to leave to the Birmingham West Campus, East Campus. There I'll be at on the Birmingham East Campus, the nursing building, which is the Ethel Hall Health Professions Building is called. And let's see, 40, right? I'll be there. I'm going over my schedule for the rest of for this week, which is the last week, by the way. I'll be in class today until 5:30, then in my office from 5:30 to 6. I'll be up here part of that time, probably sorting papers and stuff, but in my office until, I'm sure, well past 6 today. But anything you bring to me, if I'm not here or in my office, slide it under my door. Okay. Then tomorrow, last day for Tuesday, Thursday classes, I'll be in the office from 8 to 8:30 or setting up the classroom here. And then in class from 8:30 to 10:45. Then in my office from 10:45 until around 2 to 2:15. I've got an eye appointment across the street. It had been at 2 o'clock. They moved it to 2:30, so that's going to push it really tight for me to get to the Birmingham East Campus for my evening class that starts at 5. So I won't have much time in between my eye appointment and having to leave to go to the Birmingham East Campus. And then I'll be there until class is over at 6:30, but I'm usually there until pretty close to 7, just shutting down everything and getting all this stuff done. Okay, so that's Tuesday. Wednesday, finally, I think I have a normal day. That's the day finals are due to come in, but I will accept them on Thursday as well. But that's going from 8 in the morning in my office, 8 in the morning until 6 in the evening. No classes, all turning in finals. And if you come to turn in the final, anything you haven't gotten from me so far, you can pick it up then. Hopefully it'll be graded by then. Okay, like things that were turned in today. Okay, so Wednesday, 8 to 6 here on this campus, my office, 265. That's out the door here, take a left, go down the half flight of stairs, almost to the end of the hall, left office on the left is 265. Okay, that's Wednesday. Thursday, final exam day for Thursday classes, that goes from 8 in the morning. I should be here until about 4 in the afternoon. Okay, now Thursday's my last day. I haven't put in leave yet, but I'm going to. My last day on campus until fall term starts. So if I don't have some work in by Thursday, I'm not going to see it until I get back for fall. That means you got it incomplete, which probably won't go over too well at your home campus, right? But leave me the stuff, yeah, whatever. So on Thursday, I'm here from 8 in the morning until close to 4 o'clock. At 4 o'clock, I've got to go by and pick up something for that last class, and then head there, and we'll be there on the, now this again, Birmingham East Campus, Ethel Hall building, not this Ethel Hall building here, the one on Birmingham East Campus. It's also called Health Professions Building or something like that on the East Campus. I'm up on room 214, second floor, room 214. So if you don't get me everything you're going to turn in by 4 o'clock on Thursday, you're going to have to bring it to me on the Birmingham East Campus, Ethel Hall building, Health Professions Building, 214. And that's where I'll be until 6:30. After 6:30, bye-bye. Okay. So please get it to me on this campus before 4, on the other campus before 6:30. All right. Any questions on that? Normally I would have been here on Monday. That's technically too late to turn in stuff, but I would have been here and would have accepted it. But we have to have grades in. They used to be about noon on that Monday. Now they're saying we have till 2, but I'm planning not to be here. I'm going to put in leave for that last day and hopefully not be here Monday. So just to let you know that. Any questions? Yeah. Oh, and by the way, I forgot to say this. I will be here Friday, I think. Yeah, Friday's in August. So I will be here Friday. And I didn't tell my first class this. I'll be here Friday from 8 to 12. On this campus, 8 to 12 Friday. That's the drop-dead latest that you can get me something. So even if you slide something on my door on Thursday, I'll pick it up Friday morning. So I will be here Friday. I forgot. We only have Friday off June and July. That's August, so I'll be here Friday morning, 8 to 12. Not much past 12 then. Yeah. You have a question? I'm sorry?
Did you submit any work on that board?
That's the thing. This weekend I had hoped to get that done, and I got tied up with all sorts of things. Like I was saying earlier, maybe before you came in, I was working outside most of the weekend, and I got, this is the second time it's happened, got covered between fire ants and chiggers. I just got, and therefore sleep has not been easy, and even getting anything done. You'll see me up here doing this all the time today because they're better, but they were really bad. And then too, we had company, and my godson brought with him, when I had planned to do some of my work, he had his summer packet for an AP calculus course in high school, and we were working on AP calculus stuff most of my free time, Saturday and Sunday. So there went my grading time, so I didn't know that was going to happen, but it did. So yeah, I've got everything graded, but I don't have it all in Blackboard yet. So I'll be returning all the papers to you right away today, before you leave. Now, research papers I can't return to you because they periodically ask for samples of student writing, but your test I will get back to you today. Okay. Thank you. Okay. And then I'll get Blackboard updated as soon as I had almost all these graded. Most of these have been turned in today, so I'm going to be grading forever. There were a few from Cal 3 that I didn't get graded, but most of them did. All right, and here's Marjorie. All right. Does anyone else know that you didn't hear me call your name? Acknowledge your name. Okay. I think I see everybody. Okay. You probably heard all my last part of the term things. I forgot this one. I'm here Friday morning from 8 to 12. So anything you get in Thursday, even if it's after I've gone to Birmingham campus, I will see it Friday morning. So, okay. I forgot that. I forgot to tell my first class that too. Okay. Any questions before we get started today? Okay, and one thing I'm going to try to do today, We're in 11.3 and almost through with 11.3. We'll do 11.4 and hopefully finish that. And 11.5 is a long section. I don't know that we'll finish it, but where we'll start for any who are coming back to Lawson in the fall, we'll be starting in the fall at 11.6. That's where Cal 3 begins. Why they have this one section out of 11 in Cal 3, but not in the other. So that's it. So if we can get through 11.5, fine. If we can't, it's not going to be a big thing. But I do want to finish 11.3 and 4. Yes.
One more question. Okay, so next semester.
I'm sorry.
You teaching on a differential equation as well?
It's being offered. I don't know if it's going to make or not. That's the only issue. But yeah, we'll be offering it. Okay, are you a Lawson student or are you a transient? Huh?
I'm transient.
Transient. But you are planning to take it in the fall? Okay.
Both CAD 3 and differential.
What's that?
I'm going to take both CAD 3 and differential.
Okay. All right. You have to get a transient letter, you know, and all that from your school, right? Okay. Yeah. So yeah, they're both being offered. I just can't guarantee they'll make or not. But the more people who sign up for them, the more likely they are to make. So don't wait too late to sign up because they may cancel early. So yeah. What's that?
I can apply for it now.
Yeah, you can register for fall now. I can't remember if I've got to look at the schedule, make sure they still have them both on there. They've done some monkeying with the schedule. So if you don't see them, I'll try to get them added. Okay. All right. Good questions. Any other questions? All right. Where we left off last time was chapter 11, vectors in the geometry of space. 11.3 was the dot product of two vectors, and we're at the top of page 775, theorem 11.6, which is where our slide starts today. Now, don't know if you recall what we were doing before, but we were talking about projection of one vector onto another vector. Okay? Let's see if there's a picture. Yeah, something like this. No, this isn't it, but we can use this. So let's say we have vector u right here and vector v right here. And we're wanting to talk about making a projection of u onto v. Okay? Now what that means is pretend there's a really bright light an infinite distance away shining down on u, and the shadow it would cast, now it needs to be perpendicular to v. Shining down perpendicular to v, the shadow it would cast on the line of v. Now v is only this short, but its line goes infinitely. The shadow that would be here on that line, that would be projection of u onto v. Now, projection of v onto u would then be shining this way, perpendicular to u, and whatever that projection would be. Now, if perhaps v had been over here, then you shine this way, and this would be projection of u onto W2, what they call it W2. That would be the projection of u perpendicular to v. So you're shining this way. That's what we mean by projection. Okay? So, the projection using the dot product, if u and v are non-zero vectors, I don't like messing with zero vectors because they're not, to me, really vectors at all, but they have to be there, okay? Then the projection of u onto v, and this is how we write it, PROJ for projection of u onto v. So the one that you're projecting onto is a subscript, and that is a bold v, by the way, because that's a vector. This is the one you're projecting onto that one. That's the normal case, uppercase, not uppercase, but, as opposed to subscript, normal script. That would be u dot v divided by v squared times v. So basically, what this part is right here is V over magnitude of V squared. V over magnitude of V would be the unit vector in the direction of V, okay? And this would be projection, this is the dot product of those. And then you still got dividing once more by the magnitude of V. So let's go back and see if that makes sense here in our picture. U dot V, remember one expression of this would be the magnitude of U times the magnitude of V times the cosine of the angle in between. Well, sure enough, that could be the projection of U onto V, this magnitude, that magnitude. Cosine here, cosine is the adjacent side, so that is kind of making sense. That doesn't account for all of it, but at least that makes it a little bit. So let's see how we can break this down otherwise. U dot V over V squared times V, the magnitude of V squared times V. That's U dot V over magnitude of V times V over magnitude of V. This is a unit vector in the direction of the vector V, unit vector. What does this turn out being? Okay? This is a scalar number, right? U dot V is a scalar. The dot product is a scalar value divided by magnitude of V is a scalar value. So this is just some multiple K, some scalar K, and what that would be, of course, is U dot V over magnitude of V. But think about what that is. U dot V is magnitude of U times magnitude of V times cosine of the angle, but you divide out the magnitude of V, so it's just the magnitude of U times the cosine of theta. So with that in mind, let's go back to what we were looking at before. U dot V divided by magnitude of V, that is the multiplier. U dot V is the dot product of these two divided by that. That's the multiplier. It says how much of this times the unit vector V, because remember V divided by magnitude of V is the unit vector. So this would be how far that's projected. That would be it right there. The gray line from here to here is underneath this part, what they call W1. That's projection of U onto V. It would be the unit vector of V, however long that happens to be, times the multiplier, which is U dot V, divided by the magnitude of V. Okay? So the scalar K is called the component of U in the direction of V, which is exactly what this is. The component of U, see, U has a parallel to V component and a perpendicular to V component. Parallel component of U projected onto V, that is this magnitude times the unit vector in the direction of V, so that gives you exactly that way. So that's what the projection is. The gray line there, what they're calling W1, that's the projection of U onto V. And that's how we get it. Projection of U onto V. Now, my little way of trying to remember this for myself, you may not find it useful at all, but think of this, the numerator is, I think of it as V dot U, because remember, dot products can go either way, so they're commutative. U dot V divided, since this is in the denominator, V, magnitude of V squared, okay? And then since it's projected onto V, you multiply it by the vector V. So that's how I remember what goes where in what order. That's just my little system of doing it. So find the projection of U onto V, this is example 6, and the vector component of U orthogonal to V for this U and that V. Okay? 3 dimensions. I'm not going to try to draw this, okay? That would come out really ugly, I guarantee. But what would be projection of U onto V? Let me get my pen set up. Okay. That's the projection of U onto V. Okay? So the U goes here and sub V here. Right? U onto V. Okay. The upper onto the lower. Okay. What was that formula? Anyone recall? U dot V times what? Times V. Perfect. Okay? Now, let's first start with the dot product. That's a pretty easy thing to do, isn't it? What's the dot product of U and V? 21.
Minus 5.
Okay, that would be 16, right?
Minus 4.
That would be 12. So the first thing here would be a 12. Now, we got to divide by the magnitude of V squared. Now, what's the magnitude of V squared? That's actually a fairly easy thing. Okay, you certainly can. Of what, V? Yes, yeah, square it. Okay, that's certainly a good way to do it. Or the other way to think of it is the dot product of V with itself. Okay, so that would be
49 plus 1 minus 4.
okay. Now when you multiply it, minus times minus, it's plus.
Plus 4.
So that would be
54.
54. Perfect. Okay, everybody see that? You just dot that with itself, or whereas before when you did a magnitude, you took the square root of it, of the product of all of the sum of those squares. You just do the sum of the squares. 49 plus 1 plus 4. Okay? Then, okay, now, I just did a boo-boo here. When you're dealing with vectors, don't ever use a dot as a multiplier, because then that means a dot product. This is just multiplied by that. So that would be that multiplier times your vector V, which is 7. I'm going to write it this way because it's easier to write, -2. Okay? Now first, let's see if we can reduce 12 over 54, will it? By what, 2? That would be 6 over 27. One more. 3 or 2, yeah, divided by 3, 2 ninths. So that would be 2 ninths. So this would be, and this is a vector. The projection is a vector. And that would be 14 over 9, 2 over 9, -4 over 9. Okay. Were any of you expecting that to be a unit vector? Please say no. Okay. No, it's not a unit vector. Nowhere close. The first component is greater than 1, so it can't possibly be a unit vector. But that is... Oh, okay. I looked at the wrong one. So how did they get that? 14 ninths I plus 2 ninths J minus 4 ninths K. Okay? So there's the first part. Projection of U onto V. Okay? Now, and the vector component of U orthogonal to V. How are we going to get that? The vector component of U orthogonal to V. Second? Okay. There is an A, B, and C where that's true, but I don't see really where it comes from here unless you're thinking way beyond where I am. What's another one? Okay, not yet. We haven't even gotten there yet. But think of this. If this is just doing like they did in the book, this is the projection of U onto V, okay? And this is U. I'm trying to make it a lot like the one in the book was. This. Then this is projection. This is a component of U orthogonal to V. So this would be U orthogonal to V, right? Just to use some abbreviation. Now, with these three things in mind, don't you see a relationship? Say again? A little louder, I can't make it out. Okay, but isn't. Okay, what if they were oriented this way? This. Okay, you don't need the angle. What if they were this way? This is U. This is projection of U onto V, and this was the component of U orthogonal to V. Think vector addition. If this were I and that's J, this is 7I plus 4J. Wouldn't that be exactly what this is, 7I plus 4J? So in other words, this thing is this minus that. If this minus this plus this is that, then this one over here is this minus that, right? So here you have your U, and here you have your U parallel, I call it. The component of U parallel to V. So we're looking for the component perpendicular to V. So the component of U perpendicular to V would be basically U minus projection of U onto V. Do you agree with that? And then vector subtraction is a pretty easy process once you use the components. So this would be 3 is how many ninths, by the way? Say again? 3 is how many ninths? Okay, 9 ninths minus 14 ninths. Is that right? No, 3 is... No, 9 ninths is 1. Say again? 27 ninths. 27 ninths minus 14 ninths is 13 ninths, comma, I like component notation, negative 45 ninths minus 2 ninths is negative 47 ninths, and minus a minus is plus 4, 22 ninths. Now that's doing quickly in my head. Let's see what they got. 13 ninths, negative 47 ninths, 22 ninths. Yes. See how that works? Does that make sense? Kind of, a little bit. Okay. That's your easy way to do your projection. And they basically did exactly that same way. The only thing they didn't do is break the U into ninths. It's just so much easier to do the subtraction that way in my mind. All right. That's how we did it. Let's see how they did it. I think it's very similar. All right. First, the projection of U onto V is what they call W1, which is, if you take it back there, the last one. Be U dot V over the magnitude of V squared times the vector V. Now, what I can't figure out is these are all without serifs, and yet these two and that one have serifs and that one doesn't. I don't know why they use different types, but it doesn't matter. They're the same vectors. Okay? So this will be exactly what we got, 12/54 times the vector 7I plus j minus 2k. And when you reduce that, you get exactly what we did, 14 nights plus 2 nights minus 4 nights. Well, 14 nights I plus 2 nights j minus 4 nights k. Okay? Now, the vector component orthogonal of that would then be the vector u, the hypotenuse, minus the parallel projection. That will give you the perpendicular projection. And that would simply be 3i minus 5j plus 2k minus 14i plus 2 nights, 14 nights I plus 2 nights j minus 4 nights k. To me, it's easy to get those all into nights. And you get 13 nights I minus 47 nights j plus 22 nights k. And that's what we got. And there's their projection of it. Now, I'm glad they have all the fancy packages they do to twist and turn their projections around so it makes the most sense. But I never would have thought of putting the x-axis down here and the y-axis out there. And z, of course, is always up. But you're trying to make a three-dimensional projection onto a flat screen which is two-dimensional. And looking at this, u is, they've already erased the original, well, part of it, is 3 on the x, and they're doing 2, 4, 6, 8. So 3 on x would be about to here. Okay. Yeah. This is, even their nice projection is really difficult to see. Minus 5j, and I'm just assuming, yeah, these are 2, 4, 6, so 5 would be somewhere here, so this would come parallel to that axis somewhere to about there. Okay, so I guess that's it right there. To me, this look like, I guess that it could be 3, 5, and then go up 2. So go up this much from here. And that's your u. Your v, which is not showing here, would be, was that 7i? That's what it looks like. Yeah, 7i minus, no, plus j. So just 1 in the j direction. That would be right here. So that would be this tick mark here. And then, what was that? Minus k? Minus 2k. So you go down 2 from here, from that point, yeah. So that's it. So the projection of u onto v, okay? We'll shine a light down here, and that would just be your perpendicular to your v here. And the projection of u onto v would just be this little piece here, okay? Now, and that is what this answer was. 14 nights I, which is just over 1 and 5 nights, just over 1.5 in the x direction, and that would be somewhere, there's 1.5 would be here. I'll take the word for that. That doesn't quite seem close, but it is 2 nights j, just barely out here, 2 nights j, okay? And then minus 4 nights k, so less than half down. So taking the word for it, that looks like about W1, and then take this minus this and get W2, which should be the I component is about the same as that one, only in the opposite direction. No, in the same direction, okay? And minus 47 nights j That's just beyond 5, 2, 4, 5 here, and I don't see how these are adding up very well at all. And then a plus just beyond 2K, so that would be somewhere up here. I don't like their projection at all, but that's what it is. Okay. To me, the picture is less than helpful. Component notation is very helpful. Okay, but that's what you get. And just the projection is really hard to see how that works out, but I'm sure they're right. It's just a sort of bizarre orientation. So that was example 6. Okay. Now, before we get into work, there is example 7. So let's do example 7 here. A 600-pound boat sits on a ramp inclined at 30 degrees. You know what I'm going to do? Yes. This is not the correct drawing, but to keep from having to draw the boat again, I'm going to use the drawing here. Okay? A 600-pound boat, so that would be your F down. Toward the center of the earth, this would be 600 pounds. Okay, I can't write pounds. 600 pounds. That's ugly. 600 pounds pointed toward the center of the earth. Okay? Sits on a ramp inclined at 30 degrees. This is nowhere close to 30 degrees, so ramp it up a little bit and do something like this. And maybe you're close to 30 degrees now. Okay? All right. It's shown in this figure. What force is required to keep the boat from rolling down the ramp? Okay? In other words, what force do you have to exert this way to keep that boat from moving? Okay? Now, as shown here, the weight of the boat is basically your hypotenuse here. You have a component that's perpendicular to the ramp and a component that's parallel to the ramp. Okay? We want this one because you see, to keep it from going down the ramp, you have to have at least this magnitude pulling up the ramp. This component here, which would be twisted over here now, that is what the ramp is supporting here. That's the normal force. We're not worried about that. We're worried about this one. So what we're looking for here is, in their notation, W sub 1, whereas this is W sub 2. Okay? So, we're wanting to know the projection of F onto this one here. Where that is 30 degrees from the horizontal. Okay. Now, understand that their figure is at something less than 30 degrees, but this angle here is equivalent to this angle here. So this is your 30. Okay? Now, they're going to be using projections, which is fine. But it seems like to me the easy way to do the problem is if this is 30 here, then this is also 30 here, right? And if that's 30, then what is this component here? Second? What is this component right here then? If this is your angle 30, what is that component? Sine. The sine of 30 degrees. And what is the sine of 30? 1/2. And 1/2 of 600 is 300 pounds. That's what you have to exert on the boat to keep it from rolling down. Now, they go through a lot of, let's see, yeah, the projections and the magnitude squared and all like that. Just use simple sine and cosine. I see no reason to go through the other part. I know they wanted you to, and it's a fine exercise, but this is just so simple to do it this way. Here's your hypotenuse. We're looking for that leg, and that with this angle being 30, then that would be sine 30 degrees times this. And you don't have to worry about projections. And, did they even have to subtract? No, I guess not. Okay. So anyway, far easier way to do the problem. Since we're running out of days of term, let's just move on. Okay. So let's go back to work. Okay, get to work now. Okay. The work done by a constant force F acting along the line of an object is given by, now this is acting along the line of an object, okay? The magnitude of a force times this distance. Now if I'm pushing down here, the line of the object is that way, I'm pushing this way. That force is not along the line of the object. To be along the line of the object, I would need to be pushing this way because the object's moving that way. So if you are pushing along the line of the object, the work done is the magnitude of the force times the distance that it moves. Magnitude of F times PQ, which is from this point to that point, wherever it headed. Okay? So this is work is magnitude of F times magnitude of PQ when they're in the same direction. Force acting along the line of motion. When you're not acting along the line of motion, like me here, only this component is doing work. This component is actually pushing it more into the floor, which is working against you, so to speak. Now, pulling this way, then only this component is in the line of motion, and the component upward, at least pulling weight off the wheels. So it's helping you maybe a little bit if we were getting into friction and stuff. Okay, when the constant force F is not directed along the line of motion, like this, you can see from this figure here, so your force now is up like this, so I'm pulling up this way, okay? The work is done by the force is the projection of PQ onto F, here's your PQ this way, onto F, which is this way, that would be projected this way, you know, perpendicular to this, that PQ onto that, which is not how I would have, no, I'm sorry, F onto PQ, I'm sorry, I was reading it backwards. F onto PQ was the projection of this onto that vector there, which would be this amount right here, okay? Shadow of that onto PQ, this is the projection of F onto PQ times the product of PQ, I mean the magnitude of PQ. Well, this again, just like we did last time, this is the cosine of this angle here. We did sine because we were looking for that here. This is the cosine of theta times the magnitude of F. Magnitude of F times cosine of theta. It's another way to talk about that projection. Times PQ. And that would be simply from, remember, magnitude of F, magnitude of PQ times the cosine of the angle in between. That's the dot product between F and PQ. So work is simply the dot product of your force times your displacement. That's what it comes out being. To get there, we went all around our ear to get to our nose, but here, that's just simply it. The product of the force times your displacement. The notion of work is summarized in this definition. The work W done by a constant force F at its point of application, as its point of application moves along the vector, PQ is one of the following. Okay, the projection form is this: projection of F onto PQ times PQ, or F dot PQ. That's the way to go. So it's just so much easier than the other, most of the time, anyway. So here, to close a sliding door, okay, a person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees, as shown in the figure. So 60 degrees below the horizontal, that's what he's pulling on. Like what in the world he's using to pull it with. Oh, it doesn't show. He's just pulling on a fork. I was thinking, what kind of device is that? But that's just the arrow for the work. By moving, so it's a force of 50 pounds in this direction, a constant angle of 60 pounds from the horizontal there. Find the work done moving the door 12 feet to its closed position. So from here to here is 12 feet. Here to there, 12 feet. Okay? So, how would you do this? Well, this one, even though I said it before, we don't know F, well, we could do it. We could do F dot PQ if you assume that that this is the I direction, so you know the PQ would be 12I. Buy that? Okay. Then your F would be the magnitude of F, which we know, 50 pounds, times the I component is the cosine of 60 degrees, and the magnitude of F times the sine of 60 degrees is your J component, right? Now I've mixed up my notation here, but hopefully you can follow that okay. What is cosine of 60?
Cosine.
1/2. So this is 1/2. So magnitude of force was 50. So this would be the force would be the vector 25, comma, and what's sine of 60? Square root of 3 over 2. So that would be 25 root 3, right? Dot that with 12, comma, 0. It's much easier to do in component notation. And what do you have? 25 times 12, 300, plus 0. So 300 pounds. No, let's see. Work done is foot-pounds. Because this was this is in feet, and this is in pounds, so that would be foot-pounds. I put pounds feet because I didn't leave enough room for it. And sure enough, that's what they got to. All right, any questions on that? Again, they may not, let's see how they did it. I think they may have done it slightly differently from what we did. Using the projection, you can calculate the work as follows. The work is projection of PQ onto F onto PQ times the magnitude of PQ. Okay? So that would be cosine 60 times magnitude of F, which is 30. So, what was it? I've already forgotten. 50 pounds. Okay? And this certainly would be half of 50, which is 25 times the magnitude of PQ, which is 12. Yep, that was pretty quick and straightforward. Half of 50 is 25, and 25 times 12 is 300 foot-pounds. All right, that's it for 11.3. Homework exercises in 11.3, well, you don't have to do any, but if you need that to reinforce what we did today, any of the odds 3 through 9, they're all at Calc Chat, 3 is at Calc View. 11 through 17, all at Calc Chat, 13 is at Calc View, 19 is at both Calc Chat and Calc View. 21 to 35, Calc Chat, 27 or 29, Calc Chat, 31 to 35, all at Calc Chat, 31 is at Calc View. 37 to 43, they're all at Calc Chat, 37 is at Calc View, and 45 or 47 are both exploring some concepts. Both should be at Calc Chat, and then 49 should be at Calc Chat, 51 or 53 at Calc Chat. Any of the odds 55 through 61 should be at Calc Chat, and true false 63 should be at Calc Chat, 65 or 67 should be at Calc Chat, 69's are proof, and 71's a bond angle, and then 73 and 75's are proofs. If you're interested, they should all be at Calc Chat. All right. To me, this is what I think I'm going to say is the it's not last important, but this is important to cover this, because some of you may be going into physics and you'll use cross products in physics. Some of you are already there and probably already know how to do these, but let's cover this. Vectors and Geometry of Space, Chapter 11, 11.4, Cross Products of Two Vectors in Space. We'll find the cross product of two vectors in space and use the triple scalar product of three vectors in space. Okay? Interesting concept. So let's deal with cross product first. Like I said, many applications in physics, in engineering, in geometry, I'd say probably in surveying, and lots of places like that will involve finding a vector in space that is orthogonal to two other, well, maybe not surveying as much, but in physics, engineering, geometry, always interested in finding things such as that. In this section, you'll study a product that will yield such a vector. Remember, our first product was a scalar product. This scales up a vector, and you get the same vector, same direction, only scaled up in length and down in length. That's a scalar product. The dot product gave you a scalar answer to the product of two vectors, such as work. Work, energy, are scalar quantities. They're not vector quantities. In this section, we'll find a product that yields a vector, a product between two vectors that yields a vector. It's called the cross product and is most conveniently defined and calculated using the standard unit vector form. Because the cross product yields a vector, it's also called the vector product. Which can be confusing because a dot product is a product of two vectors, but it gives you a scalar answer. So sometimes they will use that. So here's how they define the cross product of two vectors in space. Let U be 1. U sub 1i plus U sub 2j plus U sub 3k. V is V sub 1i plus V sub 2j plus V sub 3k. They're both vectors in space, okay? Cross product of U and V is this vector. Don't try to memorize this. There's far easier ways to do this than trying to memorize. That would be the product. Now notice the ones are your components in the I direction, but your I direction here has not a single one, sub 1 in it, okay? It's U sub 2 times V sub 3 minus V sub 2, or U sub 3 times V sub 2. That would be the I component. Your j component, that was positive, it's going to be a negative of, and again, not a 2 here, okay, the 2's are your j components, u1 times v3 minus u3 times v1, okay? That's your j component, and your k component is, again, not a 3 in it. It would be u1 v2 minus u2 v1 with a plus in front of it. All right. It's important to note that this definition applies only to 3-dimensional vectors. If you have the 2-dimensional vectors, different. 4-dimensional vectors, whatever those would be, very different. This is only a 3-dimensional. Okay? We'll talk about the 2s and maybe higher later, but this is it. Now, yeah, here's how they say to do it. Have any of you dealt with determinants before? Maybe a long time passing or never. Okay. You're going to learn a little bit about determinants here, but actually I'm going to show you an easier way. It kind of uses determinants, but simplifies a little bit. Okay? What you do, because you're going to get a vector as an answer, write your unit vectors down first. I, J, K. That's your first row. Okay? And then whichever one shows up first here, those components go in the second row. U1, U2, U3, and what shows up here, V1, V2, V3. Okay? The components in those rows. All right. To get the I component of your cross product, okay, what you do is wipe out the first row and the first column, and then do a determinant of what's left. The determinant is kind of a cross product like thing, only it's the down diagonal minus the up diagonal. Okay? So I would say U2 times V3 minus V2 times U3. I notice they put the U3 first, comes this way. And maybe that's, I don't know. I like down diagonal, up diagonal, so I'll put that one first. And that gives you the component in the I direction. Now, when you're dealing with matrices, especially determinants of matrices, which this is, it turns out being square matrix, each position has a sign quantity associated with it, a sign characteristic. And here's how you determine plus, minus, plus, minus, plus, minus, plus, minus, plus. As long as you go horizontal or vertical, plus, plus, minus, plus, minus, plus, minus, plus, minus, plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Any way you go, as long as that, you alternate signs every time. So since the J is in a minus position, that's why the minus goes here. Okay? Without getting into anything else, just remember that. J is a minus, plus, minus, okay? That's why the plus is here. Okay, and again, wipe out the first row and the second column now, and do the determinant of what's left. U1 is minus out here now, and this is going to be the J component, U1 V3 minus V1 U3. The minus out front, U1 V3 minus, they do U3. Doesn't matter which order you multiply. That's your J component. And when you get to the K component, again, K is in the plus position, so you put a plus here, wipe out the first row and the third column, and do your determinant here, which is U2 V1, U1 V2 minus V1 U2. They flip it like that. And that's how they say to remember, and that's what gives you your cross product. I don't think they're going to show you the easy way. So I'm going to show you the easy way, if it's all right. Okay? I need more room to write. Seems like I have the most room here. Okay, here's how I suggest doing it. And this only works for 3x3s. Okay? Doesn't work for a 2x2, doesn't work for a 4x4, only works for a 3x3. Again, you start out the same way they do, I, J, K. But then, repeat the first two, I, J. You don't need the third K. And then, it's U1, U2, U3, U1, U2. Repeat the first two. And then do V1, V2, V3, yeah, V1, V2. Just like before, only repeat the first two. Okay? Now, you're going to do like a determinant, only you're going to just follow me here. Your down diagonals are always positive. So that's going to be U2, V3, I. Okay? Down diagonal, always positive, plus U3, V1, J. Down diagonal, always positive, plus U1, V2, K. All right. Up diagonals are always negative. Now, it may be helpful to erase these two. I don't usually, but just to keep from being too crowded looking. Okay, let's do our up diagonals. Minus, and this is going to be a K, minus V1 U2K. Okay? Next up diagonal, minus V2 U3J. No, I. Minus V2 U3I. Okay? And then up diagonal is always negative, minus V3 U1 J. Okay? Now, pair the things up. U2 V3 minus V2 U3 is your I component, plus U3 V1 minus V3 U1 J, plus U1 V2 minus V1 U2 K. All right. Now that's what we got that way, and let's see how that compares. U2 V3 minus V2 U3 I. Perfect. Now they put a minus here, so we'll start with the minus here. V3 U1, I did U1 V3, and then a minus, there's a plus, U3 V1 J. Perfect. And then plus U1 V2 minus U2 V1. Exactly the same. To me, the advantage of this one is you don't have to wipe out rows and columns. You don't have to remember plus minus plus. Just use the signs. Down diagonals are positive, up diagonals are negative. Now remember, some of these values can be plus or minus, but it's the down diagonals are the product of these. The positive, whatever the product of those is, whatever sign that gives you, and this would be negative, whatever product you get here. That could be a minus number, so minus would be a plus. But anyway, that's how it works. And to me, that's so much easier. And you get the same answer, to me, a lot quicker. Okay? Pay your money and take your choice. You've already paid your money. You take your choice how you're going to work this. Okay. Now, what they're going to do next, I think, is this. Notice that the minus sign in front of the J component, and if you do it my way, you don't have to notice that anymore. But each of the remaining is a 2x2 determinant that evaluated doing down diagonals are positive, up diagonals are negative. AD minus I always do CB because it's up diagonal. But it's the same answer. Okay. So what would that one be? Can you do that in your head? Negative 14. Perfect. How about that one? Stop right there. 12, right? Because you got a 0 here. Yeah. Okay. So that just be 12. So that's how you do the determinant of the little squares that are left. And you only get these if you do 3 by 3s. But you see, if you do the other method, you don't even have to worry about these. Because the signs all work out for you. If you remember, down diagonals are positive, up diagonals are negative. Now, if you have minus signs in there, it's just the positive of this minus the whatever that one is. So it would be a minus 2. This is a minus sign because it's 2 times minus 1, but it's positive of that. 2 times minus 1 is so it would be plus a minus 2, which is a minus 2, and then minus plus 12, which is a minus 12. Okay, just remember that. Okay, so let's do example 1. For u is equal to I minus 2j plus k, and v is 3i plus j minus 2k, goodness, 2v. Find each of the following. U cross v. Let me get my pen set up. So how would you do that? Which method do you want to do? You tell me. Second? The one I showed you, they didn't. What would you put across the top? I, J, K, I, J. Okay, what you put next? 1, negative 2, 1, 1, negative 2. And what would you put next? 3, 1, negative 2, 3, 1. Perfect. Okay? Then what would you do? Second? And that would be what? 4i plus 3j plus k Say again. Minus a negative 6, which is?
Plus 6.
K. Okay. I can't hear well. Next.
I minus I.
Minus I. Plus 2J. So what's your answer? 3I. Plus 5J, is that what I heard? Okay. Now, what I really want to do next is show you a check. But we haven't gotten to the check yet. So, what I think I will do is jump across. We'll leave this right there, and let's get to the check. Oh, okay. Here's, I think, where I want to be. All right. U cross V, that vector that came out of the answer, U cross V, is always perfect or orthogonal or perpendicular to U and orthogonal to V. U and V don't have to be orthogonal to each other, but they can do whatever they want to. But the cross product is going to be perpendicular to both of them. Now, what was special about perpendicular multiplications before? If you did a dot product of two perpendicular vectors, what do you get? 0. So let's go back here, and this is just a really good check. Whoops, here we go. So here was our cross product. So let's dot U and the product, and what should we get as an answer? 0. Let's see if we do. 1 times 3 is 3, minus 2 times 5 is negative 10, so that would be negative 7, right? Oh man, this doesn't look good, does it?
Or is it minus?
What's that?
Was it minus? No.
Okay, that was, woo, we may have made a mistake here, did we? 4i, let's make sure we wrote the numbers right. 1, negative 2, 1, 3, 1, negative 2. Years old. Okay. Okay. I think I wrote them right. Okay, because y'all were checking me and you wouldn't let me make a mistake, would you? 4i plus 3j. There. That is supposed to be a plus k, and I read it as a 4k. So this, is that what you were saying earlier? Somebody? Anybody? Going down here, that's plus k. I put a plus k, and it should have been a 1k. Okay. Okay? All right. And it's a plus 6 minus 1 and plus 2. Got it. So this should be a 7k, right? Sorry about that. I put a plus and thought it was a 4. Okay. Now, we'll do the dot product of these two. That would be a 3, right? Minus 10, that would be a minus 7 plus 7. Ding, ding. We got it. Then let's do this one. 9 plus 5 is 14, minus 14, 0. Very good. These two, if this is the cross product of those two, then the dot product, either one of those with this, has to be 0, because it has to be perpendicular. And that's a very, very, very easy check. And you see, I just caught myself in an error. So I'm glad I checked. Not in front of you, but no, I'm just kidding. It doesn't matter to me. So there was the A part. Let's do the B part. Okay. I'm going to leave the IJK thing there, and I'll leave this here. I'll take out those two. And let's do V cross U. Okay, I left the IJK, IJ. Now, Cole, you came in late, so if any of this is not making sense, ask a question, okay? Okay, have you done cross products before? Okay, well, ask if it's fuzzy. What we do for a cross product, it's going to be a vector is your answer. And what we do is write down I, J, K, and then repeat the first two I and J. Now, the vector that shows up first, we write those components down underneath that. So that would be a 3, because the V is next here, 3, 1, negative 2. And then repeat the first two, 3 and 1. And then your U is the second one, so it goes in the third row, and that would be a 1, negative 2, 1, 1, negative 2. Okay? Now, give me another color. Say again? Red? Okay. Try to do red, if I can get red to come up. There we go. Okay, so we're going, again, do our down diagonals are positive, so that would be 1i, negative 2j, negative 6k. Up diagonals are negative, that would be negative 1i, which sign? Negative 4i. Yeah, there's the I up there. And then negative 3j. Okay? Let's add those together, and what do we get? Negative 3i, negative 5j, negative 7k. Hey, what do you notice? That's exactly opposite the other one. Now here's the other thing about cross products. I haven't told you this yet, but let's just say you tell me a direction for U here, okay? Is it all right to put U that way? Okay, and which way is D? Okay, something like this. So if you point your fingers on your right hand toward where U is going, but bend them to where J is going, your thumb is going to be where the perpendicular to both of those is, and that's the cross product for that. But if I had started and put my right fingers toward where the V was, and then crossed them where U, looky here. The cross product is exactly opposite direction, so therefore it would be exactly opposite numbers. Same magnitude and everything else, it's just completely the opposite direction. So, that's just something to note. Now let's do V cross V. Okay, so let me erase again. Ooh, I could have left the first row. I messed that up, didn't I? Okay. And since this will have nothing to do with what we just had, I'll just erase this. Okay? Now, V cross V, okay, the IJ and K stays the same across the top. I'll go back to my dark blue or whatever it is. Okay, and then it would be a 3, 1, negative 2, 3, 1. And this would be, again, a 3, 1, negative 2, 3, 1. Because that's the same vector. V cross with itself. Okay? Let's do our, I don't need, okay, yeah. So what would be my first down diagonal? Negative 2i, negative 6j, plus 3k, up diagonal. Second, negative 3, what is that? K, okay, plus 2i, plus 6j. And what do we get? The zero vector. 0i plus 0j plus 0k, which tells you that the cross product of a vector with itself is 0. The dot product with a vector times a perpendicular or orthogonal vector is 0, but the cross product of a vector with itself is 0. The zero vector is a vector now. It's a zero vector, not the number 0, but the zero vector. Okay? And sure enough, that's what they got in the book, and they called this zero vector. Is that a unit vector, by the way? No, nowhere close. Its magnitude can't be 1 because it has no magnitude, okay? So yeah, that's not a unit vector. All right, so with that in mind, and I just showed you that U cross V is exactly the opposite of V cross U. That's what I was waving my arms about when you came in. All right, let's see how they do it. I know theirs will be fun because they do all the... So they set it up this way. This is how the book does. The way I did it was, to me, easier. Okay? They set it up here. And what you do there is, for the I, you wipe out first row, first column, and then you just take this cross product. 4 minus 1. Always positive on the down diagonal, negative on the up diagonal. 4 minus 1, that would be a 3. Well, they're not that far yet. But do that. And then the J, wipe out this one and that one. But it's always a minus, the way they do it. The way I did it, you don't have to worry about this, but the way they do it, it is. You think of this as a position being plus minus plus. So that's always going to be a minus position. So you put a minus sign there, and then wipe out that row and column. Minus 2, minus 3. Well, just write that determinant there. By the way, the solid lines, vertical lines are a determinant. Okay? And then the K would be positive because plus minus plus position. Wipe out these two and you have the determinant 1, negative 2, 3, 1. Okay? Then here it's minus 4, minus 1, is minus 5I. Well, no, I'm sorry, 4 minus 1 is 3I, sorry, I can't multiply. Minus a negative 2 minus 3, J, plus a 1 plus 6, K, and that's 3I minus a minus 5 is plus 5J plus 6K, or 7K, I can't read, okay? I can't add either. Minus 2, minus 8, minus 2 minus 3 is minus 5, so it's plus 5J plus 7K. Okay. Now, V cross U, again doing the same thing they did before. The I is the 1, negative 2, negative 2, 1, I. J would be 3, negative 2, 1, 1 times J with a minus sign in front. And the K would be 3, 1, 1, negative 2. That's the determinant there. And that would be 1 minus 4, that's a minus 3I, minus a 3 plus 2 is a minus 5J, and the next one would be the, and V cross U, you always put the first one in the second row and the second one in the third row. Got to say that. Okay. But then and that gives you minus 6, minus 1, minus 7K, which you find out is exactly the negative of part A, because you did them in the opposite order. And remember, if you do dot products in the opposite order, you get the same answer. A dot B is the same as B dot A. Doesn't matter. A cross B is exactly the opposite of B cross A. So remember that. Okay, note that the result is the negative of part A. And then when you do this one, okay, this will be a minus 2 minus the minus 2, which is plus 2, 0I, a minus 6 plus 6J minus 0J, and this will be a 3 minus 3, 0K. So yeah, you get the 0 vector. Okay? That is a vector. Bold there, I'll put an arrow over it. So here are your algebraic properties of your cross product. If U, V, and W are all vectors in space, C is any old scalar, okay? Any real number, okay? U cross V is always exactly the opposite of V cross U, always. That's an anti-commutative property, I guess you would say. On this one, U cross V cross W, no, V plus W, this is a distributive type thing, is U cross V plus U cross W. Now remember, sum of two vectors is a vector. The cross product of two vectors is a vector. Well, this is a cross product, which is a vector, added to a cross product, which is a vector. Vector plus vector is vector. So at least the things are coming out right. And sure enough, everything works out pretty much, I think, like you'd expect. Now, this is distributing a scalar across a cross product, basically. It's not really a distribution because it's sort of like a association or something. That would be Cu cross V, which you could also say is U cross CV. So put the C with one or the other. It doesn't matter which, but don't change any order. Don't flip these two because that makes it negative. But just put the C with either one of them. Now, also, U cross 0, the 0 vector, all those components are going to be 0. You're going to wind up with 0. This one, you don't need a minus sign, okay, even though it's opposite order because everything's 0 there. And U cross itself, or V cross itself, or W cross itself, always a 0 vector. Now, here's another strange one. You have a cross product here, V cross W, that's going to give you a vector. You dot that vector with another vector U, and you get exactly the same answer if you had crossed these two and dotted with that. Okay? And if you worked out what this comes to, remember this has, if you call these components V1, V2, and V3, and W1, W2, and W3, work them out that way and then cross them with dot them with the U1, U2, U3. Do that and do it to this side, you'll see they come out the same components put together. Okay? So that's how you'll wind up checking that. But these are both scalar numbers because they end up with a dot product of two vectors. So they're scalars. And they sum up to the same thing. All right, here's some more geometric properties of dot product. If U and V are non-zero vectors in space, meaning three-dimensional vectors, and let theta be an angle between U and V, okay? U cross V is orthogonal to both U and V. We showed that, okay? U cross V, the magnitude of U cross V, is the magnitude of U times the magnitude of V times the sine of the angle in between. Do you remember what the thing was if you had dot product of U and V? What was our second definition of dot product? It would be magnitude of U times magnitude of V times the cosine of the angle in between. So here's the closest thing you have a similarity, and it's a minor difference. But of course, this has to be a magnitude here because this is a scalar quantity. U cross V equals 0 if and only if U and V are scalar multiples of each other. So we saw that V cross V, or U cross U, is always going to be a 0 vector. But if U is in this direction and V is in that direction, but along the same line, that cross product is going to be 0. Okay? They are scalar multiples, and those multiples could be a minus sign. And the magnitude of U cross V is the area of the parallelogram having U and V as adjacent sides. So if you have this here and that there, then this cross, the magnitude of that cross is the area of the parallelogram. Okay. That's a sort of a surprise. That would be that. Both U cross V and V cross U are perpendicular to the plane determined by U and V. So like we said, if U was up here and V was down here, the plane that contains those two are there, the cross product is going to be perpendicular to that plane. That way or this way, however you do it. Okay. One way to remember the orientations of U, V, and U cross V is compare them with the unit vectors I, J, and K. as long as you realize that K is I cross J, and as long as you write them in this order, it works out fine, okay? I think they've left out something here. I think they've left out a few words or something. No, I guess it's okay. Yeah. I, J, and K. K happens to be I cross J. Okay? Yeah, they're getting to the right-hand system. They just have a weird way of going about it. But let me just say this while I started on. I cross J is equal to K. J cross K is equal to I. K cross I is equal to J. As long as you keep them in that order, I, J, K, I, J, sort of like what we just did, then the cross products are going to be equal. As soon as you cross one, you get a negative. J cross I is negative K. K cross J is negative I. I cross K is negative J. So as long as you keep them in the right order there, then you're fine. Okay? So if you keep up with that, then this is what you get. To me, it's so much easier to use your fingers. Okay? Not finger, but fingers. Okay? I cross J equal to K. I mean, U cross V perpendicular in that direction. Okay? The difference here is I and J are always perpendicular to each other. Here they don't have to be. Anything in the plane. I mean, even like this, that's going to be like this. Like this, it'll be like this. Like this, it'll be okay. So these two don't necessarily need to be perpendicular to each other. Just any U cross J, V, is going to be perpendicular in the right-hand relation. Three vectors U, V, and U cross V form a right-handed system, whereas the three vectors U, V, and V cross U, that then flips it over to the other direction. And here's Ricky. All right. So we're only missing Kayla, I believe. Per grade attendance, of course, it's last day of class. One you've been dreading all term. Yeah, but, okay. All right. So let's do this. Find a unit vector that is orthogonal to both U and V. How would we do this? Second? Cross product. Okay, and how would you do that? I, J, K, I, J. I've got you convinced, huh? What goes in the next one? 1, negative 4, 1, 1, negative 4, and the next one? Okay. 2, 3, 0, 2, 3. Okay? And let's do our diagonals now. 0I. 2J, 3K, up diagonals, second, 8K, negative 3I, nothing, okay? So this would be negative 3I, I can't write very well, plus 2J plus 11K is going to be orthogonal to both of those. Now we need a unit vector that is orthogonal to both of those. How would we do that? Divide by the magnitude, which is? Okay. Okay, that's pretty ugly writing, but I hope you can follow it. So let's do that denominator first. That would be,
134.
okay, 121 plus, what do we say, 13? No, yeah. 121, yeah, 134. Square root of 134. And just put that over minus 3. I just prefer this, okay, to 11. Just do it like this. So that would be negative 3 over root 134, comma, 2 over root 134, comma, 11 over root 134. Okay. Probably not the notation they will have, but hopefully that will be it. This is example 2. Negative 3 over root 34i plus 2 over root 34j plus 11 over root 134. I keep saying 34. 134k. Got it. Make sense? Okay, let's see how they did it. I think that was a little bit longer way, but we'll see. All right, the cross product U cross V, and they've shown it here. Thank you that I didn't have to do that. Okay, shown in this figure is orthogonal to both U and V. That was the cross product. Here was U and here was V. Okay. Notice V is on the XY plane because it's zero components, neither up nor down. Okay. Let's see. Okay. It's true that the cross product is orthogonal, and that's what they're saying here. Looking at the picture doesn't tell you it's orthogonal. It's just that you know that the cross product of two vectors, the cross product will be orthogonal to both. So that's what it's saying. Don't ever trust a figure, okay? Especially if you're drawing a three-dimensional graph on a two-dimensional board, you don't know where it's heading. But that is the case. Now, how you get that was here. They showed you the answer before they did the problem. And what they're going to do is the cross-outs and all that kind of stuff. Oh, no, they're not. They just don't magically give you an answer, okay? But you can almost do it. That would be minus 4 plus, or minus, this is 0, minus 4i, and then minus 3i, okay, multiply. Minus 3i, and then this will be a 0, in this case a plus 2j, yeah, and then k is going to be 3 minus 8, minus 8 is positive 11, yeah. So you can do it fairly quickly their way too. You just have to be very careful. Okay, so that's the same answer we got for the cross product. Then the magnitude of that is root 134, which is the same answer we got. And then when you take the vector and divide by its magnitude, you get unit vector, which is exactly what we got. Now, they're skipping example 3. Okay. Now, have I just run past when we usually break? By a pretty long shot, didn't we? Y'all need a break or not? Like to have one? Okay. Now, if any of you are leaving at break, I mean, this doesn't get you in trouble because there is no trouble. You're adults, you do whatever you want. But be sure that I give you your papers back before you go. Or any of you planning to not come back after break? Okay. All right, we see who the troublemakers are, don't we? Okay, before we do that too, something that Anthony pointed out, let's see, I don't remember your first question on the test, on test 3. Oh, okay, I do remember it. Did everyone get a copy of the last test, which is test 3? Any of you do not have that? Okay, if you pull it out, if you got it with you, pull it out, and this is just sort of a reference type answer. The number 1 is the first 5 terms of a sequence. Sequence are things separated by commas. The second question says the first 5 terms of the sequence of partial sums. Okay? So the first partial sum would just be the first number. The second partial sum would be the sum of the first 2 numbers. Third partial sum was the sum of the first 3 numbers. A sequence is a sum, not just, those things are separated by plus signs. So that was that. All right. Number 5, Anthony discovered, and I realized I goofed up on, is the fact that I left off the equations. Number 4 gave you the equation. X is t squared, y is equal to 10 minus 4t. Then number 5, I didn't give you the equations. And now I've got to find, oh, here they are. And here's what they are. And while I've still got this up, let me find some white space somewhere. Ah, there was some. Okay. So people who aren't here will hear this too, that one person who's not here. Number 5 on test 3. Test 3, number 5. Okay? It says find dy dx and d2y dt, dy dx and dy d2y dt squared, if possible, and find the slope and concavity, if possible, at a point corresponding to t equal 4. But then I didn't give you the equations. So here are your parametric equations for number 5. X equal t plus 2. Pretty simple parametric equation. And y is equal to t squared plus 6t. Okay. So did everybody get that? Okay.
No, suppose you assume that you took from number 4 and then worked from there.
Okay, if you took number 4, then the first question would be exactly the same.
That's right. That's what I assume that you pulled on.
Oh, okay. So did you already turn it in?
That's the way I turned it in.
Okay, well, okay, if you did, let me give it back to you. Because you just turned it in today, right?
Yeah.
I was thinking that was your last test. Okay, here you go. Anyone else already turned in test 3? Yeah, I want all of you to have opportunity to see that. Okay. So that was question number 5. Okay. Now, let me see if I can get this back in the order it needs to be in. Otherwise, I'll never find my way again. Okay. Let me, since some of you will be leaving at halftime, and we're past halftime, sorry about that. It was just such good stuff, I couldn't help it. Okay. Oh, wait, I went too far. Okay, I can't return your research papers because periodically they do ask for samples of student writing. I think I've already returned test 1 to everybody. I hope so, because I don't have any in here. Test 2, it takes me a while to get through the stack to find them. Now, some of you, I think, turned in test 2 today. Have any of you not turned in test 2, period? Any of you still holding? Okay, you've got it now. Okay. Okay. Oh, y'all are. Okay. You do test 1. No, this. sorry, you returned it. Here's test one. Someone's turning in test one now, right? Okay. Corey. Cameron. Marjorie. Kayla's not here. On the grade book right here. Right there. Fantastic. Okay. Test one, sorry. Okay. Jay? That's right, I remember now. I couldn't return test one because I didn't have them on my list. But, I have to. Stokes? Okay. Wrong? All right, that's all test ones. Anyone didn't get one that was expecting one? Okay. Test two. Now, has everyone turned in test two so far? All right, here are the test twos I have. Everybody else turned in test two, right? It's not here. Okay. 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 That's all I've got for test two. And then a few people have turned in test three today, so obviously I haven't graded those. All right. All right, ready for your break? All right, then let's take a quick one. Okay, all right.
You must so you probably have a grade.
I'm sorry?
You probably have a grade the other test too.
The other test?
Test two.
Test two? When did you turn it in?
I turned it in last week. Or, yeah, last week.
I thought I graded everything I had.
Yeah, I turned it in.
Okay. Okay. Especially people who are Marjorie, check and make sure his didn't attach to your test tube. If you did have a real thick one. Oh, you just turned in your test tube, right?
Yeah, that's just how it works.
That's all of it? Okay. See if it was attached to. It was the one student I didn't have. Let me see first if I test two. I haven't graded it because it's not in here, so, but I don't know where it is. Well, wait, let me see. Maybe I hadn't finished grading all of. There's your test. You turn in, oh, here's the test tube right here. Wait. Corey, I'm sorry. I'm looking at that. Okay, I was looking at the wrong one. Corey. Yeah, I didn't have you test two. I must have given it to somebody else. Yeah, I got yours. But I didn't just pass it out. Okay, well, let me see. It's all this has been turned in today. Let's see if it got put in with, for some reason, got in with Cal 3. I can tell you your score, but right now I can't find your paper.
Okay, you know the score.
Okay, let me. Got a 91 on test 1, right? Mm-hmm. 95 on test 2. Okay, hold on, let me see if it's here somehow. 86. See, the other thing is that it somehow got mixed in with Cal 3. There's Taylor. I'll probably find it, so when you turn in your final, if I found it, I'll let you know. I don't know where it could be, because I got your score in, but where the test is, unless it got stuck on somebody else's paper clip. Okay, sorry about that. Okay, now back. Do y'all need a break? Yay or nay? Okay. But would y'all have a serious objection? Let's see. I do want to mark where I left off. I think we had done example 2, but we had not done example 3, right? Is that where we were? Okay. Since we've lost about half the class or more, and for those who may be returning for Cal 3 here, would you have any objection if we just stopped here and we'll pick up there in Cal 3, any who may be back, which I think is only one of us that are still in the room, have any objection to that? I didn't quite get to finish grading Cal 3 test, and I only have 5 minutes between classes, so I'd like to have the time to do that, and since we've covered everything that's on the test, would y'all have a big objection to? I mean, I know I'm cheating you out of some of your tuition dollars, and I know you'll probably be writing me up before the academic dean, but I can handle it. I'm not going to be here that much longer anyway, okay? So do you mind? Have you done student course evaluations? All right, good deal. And and don't count me off too bad for this. I should have asked that first. Okay, never mind. Okay, but anyway, we'll go from here. And I've really enjoyed having y'all in class. It's been a good term, good thing. We got, I think, a lot covered. Wish we had gotten a little bit more toward the end, but I don't have to let you go early if that's okay. Get over it. Okay. All right, good deal. So I'm really sorry that I'm cheating you out of that, and hopefully you won't need it when you, even more important than that, when you get to Cal 3 at whatever school you're going, that you won't have a big gap here. It's not much of a gap, but it's just a little bit. But I think what we've done, you can figure out anything that's in between. Okay, so we'll pick up here for those who are going to be back here in the fall or whenever you take it next. we'll start at example 3. All right, good deal. And like I said, I really enjoyed having y'all in class. Take care, good luck next year, and keep it firing. Keep in touch, come back. We'll be glad to see you. All right.
Are you going to be in class, like during our class time on Wednesday?
I won't be here. I'll be down in my office,
Okay.
more than likely, unless someone has some big question. I need to come up and project something or something. I should be in my office. Yes, sir.
I slipped my paper under your door on Thursday, I think, on the 2. Did you get my paper?
Yeah, I believe I did.
If not, I have another copy today.
I don't think I've rated it yet, but yeah, I got it. It was this morning, wasn't it? I mean, I would have seen it first thing this morning.
I guess so.
Yeah, right, because I'm pretty sure if you want to wait just a minute, I will check and see, because I believe that was near the top of my stack here. This is all stuff that was turned in today. Oh, there, yeah, I've already given you a 0. No, here it is, right there. And your attachment too.
What's the right number?
Okay.
Number now.
Okay. You're in loss state, right?
That's what my old teacher
This is
told me.
one way. The easiest way would be check your email.
I didn't know if it was a number or if it was up or down. It's
Yeah.
like in my Cal one teachers usually ask for like a number. So
Yeah, yeah.
Alright.
So I think that's it.
Okay.
But, yeah, I think I am going to try it.
Oh, there's. How do you spell
I
that?
checked it like 40
Oh.
times the past 2 days.
Yeah, you should be good. You're like, I'm done.
Let's see, 3. 3 is give her T, right?
Okay, try
Yes.
that.
So you said it was
You know how to log in?
y equals 727. Yes.
Let's make it very easy. Okay, check any of these from 3 days. No, but scroll up. Oh, there it is. Okay. Survey content. Yeah, that should do it.
Got a giant fraction.
Yeah, I went ahead and made it into a decimal.
Click here, I think it's the link.
Let's make it 1,000.
All right. Y'all. Oh,
Yes, I have my last test.
yes, I have no bananas. Okay. Good deal. Thank you.
Still thinking
Oh,
about it. I
okay.
want to check it over one more time and bring it Wednesday or if I
That'll
want
be
to
fine.
do it.
What hours do you have office hours tomorrow?
Tomorrow,
Yes,
10:45 until about 4:15. No, well, 10:45 until around 2:15 because I've got an eye appointment tomorrow at 2:30.
and then Wednesday?
Wednesday, 8 to 6.
And you'll be at this campus on Wednesday? Or
Yeah, this campus all day Wednesday,
Okay.
8 to 6.
Awesome.
Yeah.
Okay. And
Okay.
okay. Bring it back on Wednesday.
Okay.
So
All righty.
I'll see you
Sounds good.
sometime during that time.
All right. Good deal.
All right. Have a good day.
All right. Thank you.